We are going to discuss Unit 2 in Mathematical Physics. So this is about complex number. And of course we have learned about a complex number which consists of real part and imaginary part. Maybe in UG or in plus 2 we would have learned about complex numbers. So which will contain real part and imaginary part. So imaginary part is represented with I always. The complex conjugate of I will be always minus I. In day-to-day life, we always deal with real numbers. So we know about numbers which are very real. For example, when you take 2, 3, 4, 5, they are all real numbers. Suppose we want to count the stones. We will always go with only real numbers, 1 to 50. We will count it. Suppose we are going to think about the fraction. If I think about 2 by 3 stone, 4 by 3 stone, it is meaningless. But if I want to know the ratio of different stones, then the ratio of the numbers will have some account. Similarly, when I talk about the mass, any mass will be always a positive number. If I say minus 50 kg, it is meaningless. If I say 50 kg, it is meaningful. If I say negative numbers, it is meaningless. But whenever we talk about credits and debits, then negative numbers exist. So similarly, some numbers that will have imaginary part, that will have real meanings. So in quantum mechanics, this complex number will have large values, and heat equation, heat diffusion, and all those things, this complex number will play a major role. So in this class, we are going to discuss about the complex number, which are very, very useful, especially in quantum mechanics, which you are going to study in the next semester. So these are the topics that we are going to cover under complex number. So review of complex numbers. We are going to have some review, whatever that you have learned earlier. This is like addition of complex numbers, subtraction of complex numbers, then multiplication of complex numbers, division, how you are going to divide two complex numbers. So that we are going to have some review about the complex numbers. And of course, most probably you would have learned about de Moivre's theorem. You would have learned. Then function of a complex variable, differentiability, analytic functions, which are very, very important one, analytic functions, harmonic functions, complex integration, contour integration, Cauchy-Riemann conditions, singular points, Cauchy's integral theorem, and integral formula, Taylor series, Lorentz expansion, zeros and poles, residue theorem and its applications, potential theory. So these are all applications. Potential theory, the first application will be electrostatic fields and complex potentials, parallel plates, coaxial cylinders, and an annular region. And the second application will be heat problems, parallel plates and coaxial cylinders. So these are the topics that we are going to cover under complex numbers. First we will have some review about the complex numbers. So algebraic operations like addition, multiplication and all those things. So you have a complex number which is denoted by Z. Usually Z denotes a complex number which will have real part and imaginary part. So Z equals x plus iy. X is a real number, iy. So this is your real part and this is your imaginary part. Okay. So usually Z equals x plus iy, but we are going to add two complex numbers. So Z1 equals x1 plus iy1, which can be represented in terms of bracket x1 comma y1. So we are going to have this representation. X1 comma y1 means x1 comma iy1. It is x1 plus iy1. Okay. So this is the notation that we are going to follow in the unit. See, I repeat, x1 equals x1 plus i1 means x1 comma y1, this bracket. Okay. x2 equals z2 equals x2 plus iy2. This can be represented x2 comma y2. Now you are going to add these two complex numbers, and in terms of real part and imaginary part, we can write like this. This is your z1 and this is your z2. Now you are going to add real part with real part, imaginary part with imaginary part. So you can add x1 plus x2 real part, imaginary part with imaginary part. This can be represented in the notation x1 plus x2 comma y1 plus y2. So simply this is addition. Okay. Now we will go for subtraction. When you are going to subtract from one complex number into another complex number, for example, z1 is considered as x1 plus I y1, z2 equals x2 plus I y2. Now z1 minus z2. So you are going to subtract from one complex number into another complex number. So which is equal to x1 plus I y1 minus x1 plus I y1. So real part, now as usual we are going to subtract. So real part with real part, that will give you x1 minus x2 plus I y1 minus y2. So this can be represented as x1 minus x2 comma y1 minus y2 in that notation. Okay, so it's given us the difference of two complex number is the complex number which its real parts as a difference of real parts. So this is your difference of real parts, and this must be your difference of imaginary parts. Okay. Multiplication. When you are going to multiply two complex numbers, z1 and z2. z1 is represented as x1 comma y1, z2 is represented as x2 comma y2. Now you are going to multiply this complex number with another complex number. So that will be given as exactly like this. So you are going to multiply x1 with x2, then x1 with I y2, then y1 with x2, then y1 with y2. Okay, I y1 with I y2. So that will give you, and we are going to separate the real part and imaginary part. That will give you x1 with x2, that will be x1 x2. Okay, similarly I y1 multiplied by I y2 will be I squared is minus 1. Okay, I squared equals minus 1. So minus y1 y2, so that will become a real number because I is not there. So minus y1 y2 plus, and your remaining term with I. So I will be x1 y2 minus x2 y1. So this can be represented exactly like this. So you have now four terms. Okay, x1 with x2, x1 with I y2, I y1 with x2, I y1 with I y2. So you will have four terms. So we have four terms now. Now division. Division of a vector quantity. Suppose when you are going to divide vector quantity, usually we know that this contains direction and magnitude. So we know about vector quantity. We can divide a magnitude, but we can't divide a direction. It is meaningless. Similarly, dividing a complex number is always, it's a meaningless. We can't divide any complex number. So for that we have small technique. Now we are going to have a division. So z1 is given as this, z2 is given as this. So z1 by z2 is given by this. Now as I said, dividing a complex number is meaningless. So what we are going to do is just take the complex conjugate and multiply. Just take the complex conjugate. So you have of the denominator x2 plus I y2, take the complex conjugate, it is x2 minus I y2, and multiply and divide by the same complex conjugate of the denominator. So that will give you this one. Now when you are going to multiply these two, will give you numerator. When you are going to multiply these two, will be always a real number, because we know that a squared minus b squared equals a plus b, a minus b. We know already. Am I correct? A squared minus b squared will be a plus b, a minus b. But here a squared plus b squared is there. So it will be always a plus ib multiplied by a minus ib. I repeat, a squared minus b squared equals a plus b, a minus b multiplied by a minus b. A squared plus b squared will be a plus ib multiplied by a minus ib. So this will become a real number. As I said just now it has become a real number. So as I said just now that dividing by a complex number is meaningless. Now we can divide by the real number. It is meaningful. Any doubt? So we can't divide by the complex number. We will have to take the complex conjugate of the denominator and multiply. You will get the real number in the denominator. So this is the way. Now de Moivre's theorem. So it says about, suppose we have this is z equals x plus iy. We can convert into polar coordinates. Okay, r comma theta. So they are all called organ diagrams. Suppose when you are going for z equals x plus iy, x is in the x-axis y will be in the y-axis usually in Cartesian coordinates. Here real part will be in the x-axis, imaginary part will be in the y-axis. Okay, here for any, this is called the organ plane. Organ plane. So this term, this is like Cartesian plane, so this is organ plane. So in polar coordinates, this can be written as z equals r cos theta plus I sin theta. It's a complex number in polar coordinates. Ordinary Cartesian coordinates, it will be z equals x plus iy. Whereas in polar coordinates, this can be written as, any complex number can be written as exactly like this. Now you are going to raise the complex number to the power n. You are going to raise the complex number to the power n. You are going to raise it on both sides. So z to the power n, which is equal to r to the power n. Here you are going to raise to the power n. Correct? You are going to raise to the power. So according to the de Moivre theorem, this n will come here. So cos n theta plus I sin n theta. So this is your de Moivre theorem, where n will be always a positive number, will be greater than or equal to 1. It's a positive number. For example, just take this example. You are going to raise it to the power 3. 3 is greater than 1 or equal to 1. So this is greater than 1. N equals greater than or equal to 1. So 3 is greater than 1. Okay. So now z equals 2 cos 20 degree. Okay, plus I sin 20 degree. Now according to this formula, that n should come front. So n theta. So this becomes 3 into 20. 3 into 20 here. Here 2 to the power 3. Z equal to r to the power n. So here 2 to the power 3. 2 to the power is 3 is nothing but 8. 3 20s are 60. So cos 60 plus I sin 60. The answer will be 1 by 2. Here the answer will be root 3 by 2. So 8 multiplied by 1 by 2 plus I root 3 by 2 will give you 4 plus I 4 root 3. So this is de Moivre theorem. Okay. Now the real complex number that we are going to learn is function of a complex variable. We know that z equals x plus iy. Any complex number is written as your real part plus imaginary part. We know already. Now we are going to talk about the function of a complex variable. Function of a complex variable is usually written as w equals u plus iv. Z equals x plus iy, we know already. Any complex number is written as exactly like this. Now the function of a complex number is written as w equals f of z. W equals f of z, where w equals u plus iv. U is the function of x and y and v is the function of x and y. I repeat, see here, this is a function of a complex number. Any f of z is a function of a complex number, complex variable. So w equals f of z is nothing but a function of a complex variable, where z equals x plus iy and w equals u plus iv. U is the function of x comma y, v is also a function of x comma y. Okay, so that's why w equals f of z is nothing but function of a complex variable. Okay, so for every variable of z in certain domain D, there corresponds one or more values of w in a well defined way. Then is said to be a function of a complex variable in the domain and is written as w equals f of z. The function itself is generally a complex valued and can also be written as the sum of its real part and imaginary parts. So your w equals f of z, which is equal to u of z plus iv of z. And z stands for x plus iy. Here also z is nothing but x plus iy. So then generally we can write u of x comma y, iv of x comma y. So that's a function. So this is your complex number, okay, complex variable, and this is your function of a complex variable. So you have to differentiate these two. Very important one. Z is a complex number, okay, whereas w equals f of z is nothing but function of a complex variable. As u and v are both functions of x comma y, that's why I said u of x comma y, v of x comma y. This definition implies that a function of a complex variable z is exactly same thing as a complex function. So u which depends on x comma y plus iv, this is a function of x comma y of two variables x and y. For each value of z, there corresponds only one value of w, then the function is said to be single value. It can be a single valued function or it can be a multiple valued function. If there exists only one function, only one value of w, then what we call this as single value. Suppose if the function takes more than one value corresponding to the value of z, then that function is known as multiple valued function, multi-valued function. Okay. For example, function of a complex variable, so which is defined as w equals f of z. Suppose if we consider z equal to x plus iy, and we know that w equals u plus iv. So w equals f of z, which is equal to u of z plus iv of z, which is written as u, which is a function of x comma y, plus iv is a function of x comma y. So we know already these definitions very well. Suppose you are going to have f of z equal to z square. I am going to consider one example, f of z equal to z square. What is f of z? X plus iy. What is squared? Z squared is given. So z squared is given. So x plus iy whole square. So x plus iy whole square is nothing but x squared plus I squared y squared plus 2ixy. So we know about this. I squared is nothing but minus 1, minus 1. I squared is nothing but minus 1. So you have x squared minus y squared plus 2ixy. Is it okay? What is the real part? Real part will be x squared minus y squared. Imaginary part will be 2xy. 2xy. See, I repeat, I squared is minus 1. So you have x squared minus y squared. So both are real numbers. X squared minus y squared. So that will be considered as a real part. And this will be 2ixy. So 2ixy, the imaginary part will be 2xy. So real part is this one, imaginary part is this one. Real part is denoted as u, the imaginary part is denoted as v. So in this expression, f of z equal to z square, your u will be this one, v will be this one. Any doubt? Now differentiability. Suppose if we have any function f of z, it must be differentiable with a limit. There must be some limit, it should be differentiable. Differential means there must be some continuous. So three things are involved in the differentiation. So a function is differentiability means the first point is it must be continuous with a limit. There must be limit will be there. Okay, but everything will contain in a domain. In the domain only will exist. Let f of z be any single valued function of a complex variable z defined in the domain D of the ordered plane. Suppose you are going to consider. Then the function f of z is said to be differentiable at the point z0 of the domain in the limit is given by this. So this is the definition for your differentiability. This will exist. So f dash of z0, which is equal to limit del z tends to 0, your f of z0 plus del z minus f of z0 divided by del z. This function should exist for any differentiability. Okay, it's very, very important concept. Often we'll be using this one. So this is a definition for your differentiability. Okay, suppose if it is z0, suppose we are going to consider as u, for example. So f dash of u, what is f dash of u? It is nothing but du by dz. Okay, so this means dz0 by dz. Okay, so f dash it means. So at the time you will have u plus del u minus u0 divided by u. So something like that. Okay, which we are going to see now. So this limit is then called a derivative of f of z. So f of z, the derivative of f of z is nothing but f dash of z. So it means d by dz, df by dz. Okay, dz0 by dz. So derivative of f of z at the point z equal to z0, setting z0 plus del z equal to z. What does it mean? z0 minus z equal to del z. See, z0 plus del z equal to z, it implies that z0, see del z, we just consider del z. Del z will be z minus z0. So it's okay. X minus x0 will be your dx. x1 minus x2 will be your dx. We have learnt already. So similarly here, del z is nothing but z minus z naught. So we have del z equal to z minus z naught. We may define the differentiability as follows. The function f of z is said to be differentiable at the point z naught in the domain D of the organ plane for every positive real number which belongs to R. There exists a positive real number such that this condition should be satisfied. Okay, these conditions should be satisfied for every real number. Okay, so you will get the answer as a real number. So for all the points z of a domain D satisfying this condition, the function f of z is said to be differentiable at the point z naught of a domain D in the limit. So that's why I said that limit must be there. So we have a limit here. Okay. So we have limit here. So your f dash of z naught, which is equal to, this is the definition for your differentiability that will exist. So provided that z is also a point of domain D, this limit is then called as a derivative of f of z at the point z equal to z naught. So you will have to have differentiation where that point will exist with a limit. This definition implies that z may approach z naught for any direction. So z tends to z naught. It means, hence the differentiability means that along whatever the path z approaches z naught, the derivative f dash of z naught always approaches a unique value. Now analytic function. We are going to consider an analytic function if it is differentiable. There exists differentiation, it means it's an analytic. So remember like this. Okay, it's very simple idea. Suppose you have a function, you are going to differentiate, it means that it is an analytic function. Suppose if there is no answer, then we say that it is not analytic function. That's all. Simple idea. Is it clear? You are going to differentiate a function. If there exists answer, what we call this as analytic function. If it is not there, not analytic function. But there must be, for any complex number, we will have to have some differentiation, some value should exist. The complex variable function f of z is said to be analytic if it satisfies the following conditions. So it must be a single value. It must be a single value. For one domain, there must be a single value. For one point, there must be a single value. F of z should have a unique derivative. That's why I said we will have to differentiate the function derivative with respect to z at each point of its domain D. F of z should satisfy Cauchy-Riemann equation, which you are going to see within 5 minutes. Cauchy-Riemann equation. It has to satisfy. So the first point is you will have to single valued. Second one is it should be differentiable and it should satisfy CR equation. Cauchy-Riemann equation, short name is CR equation. So it has to satisfy CR equation. An analytic function is also known as, then many names are there, holomorphic, or sometimes we call this as monogenetic function, analytic function. But general name is analytic function. Usually you will say that analytic function for any complex number, it is exactly termed as differentiable, single value, and it should satisfy CR equation. Okay. For example, f of z equal to z squared. We are going to check it is analytic function or not. We are going to check whether it is analytic function or not. So f of z equal to z squared means z equals x plus iy, we know already. So f of z equals x plus iy whole squared. So just to square it will give you this x squared plus I squared y squared plus 2ixy, we know already. I squared is nothing but minus. So you have minus 1. So you have x squared minus y squared plus 2ixy. So this is your real part and this must be your imaginary part. So u is termed as x squared minus y squared, where v will be 2xy. And this equation, Cauchy-Riemann equation, is this one, which we are going to see now. Okay, after this slide we are going to see. So this is your Cauchy-Riemann equation. It has to satisfy this Cauchy-Riemann equation. Here it is given as partial. See, it is not d. It is partial du by dx because there are more than one variable. Two variables are there, x and y. So that's the reason that we have used only partial differentiation. So partial du by dx, which is equal to partial dv by dy. Partial du by dy, which is equal to minus partial dv by dx. You will have to remember these equations, which are very, very important. So you have to remember. So these equations are called CR equation, Cauchy-Riemann equation. So it has to satisfy this function. So this function should satisfy this equation. Only then it is analytic. That's all. So you have now u equals x squared minus y squared. V equals 2xy. So now you are going to differentiate with respect to x. When you are going to differentiate with respect to x, that will give you 2x minus 0. So you have 2x squared is nothing but 2x. Similarly, when you are going to differentiate this with respect to x, which is nothing but 2y. 2xy is given as 2y. When you are going to differentiate this with respect to y, this becomes 0 minus 2y. When you are going to differentiate this with respect to y, will give you 2x. You just check whether it satisfies or not. Just check whether it satisfies or not. Just go with the crossed one. Du by dx, partial du by dx, which is equal to dv by dy. Du by dx equal to dv by dy. See, you check, just check. They are equal. 2x is equal to 2x. So they are equal. So one equation is satisfied. And what of the other one? Du by dy, which is equal to minus dv by dx. See, you just check these two. Du by dy equals minus 2y, whereas dv by dx equal to plus 2y. So exactly 2y equals minus 2y. So it satisfies. So this is your analytic function. F of z equals z squared is an analytic function. Any doubt? Simple one. You have the function f of z is z squared. You substitute z equal to x plus iy. Separate into real part and imaginary part. Then you will have to use Cauchy-Riemann equation, differentiate, and if this condition is satisfied, we can say that the function is analytic. That's all. Very, very important question. It may appear in short questions. Okay, in your exam, semester exams. Any doubt on this slide? Now we'll go for the second problem. F of z equals e power minus x cos y plus I e power minus x sin y. Okay, so here the real part is given as u equals e power minus x cos y, and your v will be e power minus x sin y. Now we will have to use only Cauchy-Riemann equation. So differentiate du with respect to x. So du by dx equals, you are going to differentiate, and this contains only y, this contains x. So keeping this as constant, because we are going to differentiate only with respect to x. So e power minus x, we are going to differentiate, that will become minus e power minus x. When you are going to differentiate this with respect to y, so e power minus x will be there as it is. We are going to differentiate cos y becomes minus sin y. See, minus sin y. Correct? Any doubt? No. B equals e power minus x sin y. Just to differentiate with respect to x. So that will give you minus e power minus x, keeping this as constant because it contains only y. Similarly, we are going to differentiate this with respect to y. So dv by dy equals e power minus x as it is. Differentiating sin y will give you cos y. Is it okay? Any doubt? Now you just apply CR equation, Cauchy-Riemann equation. So du by dx equal to dv by dy. Whether they are equal? They are not equal. Correct? They are not equal. Right hand side. Right hand side. Look at the right hand side. They are not equal. So immediately you can say that this is not analytic equation. This is not analytic function because doesn't satisfy CR equation. See, any doubt? Very simple one. Now we are going to derive Cauchy-Riemann conditions. It's very, very important, big question. Okay, 10 mark questions, very, very important. We are going to derive these equations. So these equations are called Cauchy-Riemann equations. So we are going to derive now. Okay. So the thing is, we are going to have a complex number. First point. Second one is function. We are going to have a complex function. Second one. And third one is differentiability. So we are going to have a differentiation here. Whatever we have learned, okay, that we are going to apply here. So third one is differentiation. And fourth one is del z. We know that z equals x plus iy. We know already. Correct? We know already. What is del z? Del z will be del x plus I del y. Simple logic. Your z will be x plus iy. So your del z will be del x plus I del y. The condition is you just keep del x exists, del y is equal to 0. We will have some conditions. We are going to have some conditions. The next condition will be keep del x equal to 0, del y exists. Okay, we will have certain equations. We are going to equate those two equations, those two conditions, we will get the answer.